This is Dr. Wood with Citadel Civil Engineering. This is CIVL203 Dynamics. Learning Objective 2.4.2, we're talking about curvilinear kinematics, and in this case, we're looking at the path coordinate system. So what's going to happen here is that we're used to thinking of our coordinate systems in terms of the Cartesian coordinate system, and that's a totally fine way to do it. But when we think about it in terms of path coordinate system, this is very powerful for curvilinear kinematics. So with a path coordinate system, what we're going to have is our orthogonal system will consist of tangential and normal components. And the way we'll indicate that is with a unit vector. So the unit vector that Bjorn Johnson and your FE reference handbook uses is an E. So in statics, if you use the Hibbler textbook, he would have used a mu with a little hat over it. Well, we're going to use an E with a little hat over it and a subscript of a T here. For the normal direction, it'd be like that. And so what do I mean by tangential and normal? Well, this tangential unit vector is always tangential to the path. Okay, and so if we think, if I use my finger as the tangential unit vector, as I'm going along this path, that unit vector is always going to point tangential to the path, okay, along the path. And the normal unit vector is, unsurprisingly, normal to the path, so perpendicular to the path. And so if we think about it, I can have a little unit vector here. So this is my unit vector system, and you can see where I've got my tangential unit vector and my normal unit vector. But as we move our way along, it's gonna behave like so. So I'm gonna have my tangential component and my normal component. Now I will say I didn't do that quite right, because the normal component we assume always points toward the center of curvature. So if we notice here, there's a curve, and so the normal direction is going to be back toward the center. So it actually start off something like this. And then when we hit that inflection point, the curvature would flip. And then another inflection point and the curvature would flip again. If we look at this in our slide, so again, we're still in chapter 11.2, 5A, 11.5A now in Bjorn Johnson's textbook. We can think about our coordinate system here, but we're going to have these components. So when we look at it in terms of the tangential or along the path component, the component that's along the path, the important thing to recognize here is that all the kinematic properties are going to be rectilinear along the path. So we already know a whole bunch about rectilinear motion now. And what we're going to be doing here is continue to do that along the path. And we actually said this in our very first definitional terms, that when we talked about things being scalar and rectilinear along the path, that's exactly what we mean here. And so if we think about our velocity, our kinematic relationship is going to show that the velocity is equal to ds dt in the tangential direction. Now you remember that we said velocity was always forward, it was always tangential to the motion, and so that's what we're seeing right here, is that ds dt in the tangential direction. Now when we take those derivatives again, math happens and we have to take the derivative of a now changing tangential component. But that's okay, there's no problem there. It still works out, velocity is always tangent. Now when we think of the acceleration, we're going to look at that tangential portion of the acceleration is going to be the same rectilinear relationship we've talked about before. Okay, and so that's pretty easy in the grand scheme of things, because this is exactly what we've done before. Now, when we said the velocity was always tangential, when we look at the normal components, the normal acceleration is what changes direction. Normal acceleration changes the direction. And so if we break apart that acceleration component, so there's my tangential and the normal coordinate system at that location. And when we break it into pieces, we'll see that there's a little bit that's showing that our speed is slowing down. That's this guy down here. And then we're also going to have our normal component. And so because velocity is 100% in the tangential direction, there is no velocity in the normal direction, but we will have acceleration in the normal direction that is changing the direction of our motion. And so that normal acceleration, again, Beer and Johnson, chapter 11.5a gives the derivation for this, but it ends up looking like this. V squared over rho, where V is the velocity, right here, ds dt, squared divided by the radius of curvature. And so if you look on my chart here, this over here is my radius of curvature. So if I zoom in so that you can see the board real nice, we've talked about our tangential unit vector, and the velocity is 100% in the tangential direction. So if we want to do velocity over here, it's going to just simply be, at any given point, v equal to ds dt in the tangential direction. And that's in your FE reference handbook on page 78. And the acceleration is going to consist of both the tangential and the normal components of the acceleration. So our acceleration will equal dv dt. That would be our tangential acceleration, the change in the speed, plus the normal acceleration, v squared over rho, in the normal direction. And if we were to find the total acceleration, we'd have to do the square root of the sum of the squares of those two components, because it's still an orthogonal coordinate system. So dv dt and v squared over rho. If you want to memorize something, v squared over rho is the thing to memorize for our normal direction, radius of curvature. And so that's really what we got going on there. So we can talk about a couple of different examples. So let's look at some examples here. I've got a nice little Pocket Lab experiment set up in which we have a swinging pendulum. So I think everybody's experienced a swing at some point. I hope. If not, go find a playground that's open. I don't know. This is recorded during the coronavirus of 2020, so maybe you can't find a playground. But if you can, find a playground and swing. And what you'll notice is that you feel heavier as you go through the bottom of the swing. And that's exactly what we see here. This little sensor is measuring in the y direction. It's measuring the acceleration due to gravity, but it maximizes when the acceleration in the x direction stops. So you're picking up speed in the normal direction. That's the x direction. So as we come down, we're picking up speed, and then we start to lose speed. And then we pick up speed in the negative direction, and then we lose speed. And so when my x is 0 here, I get a peak in the acceleration that's equal to gravity, about 9.81, plus v squared over rho. And so that's because you're going the fastest through the bottom. And that sensation of kind of like weightlessness at the end of the swing, that's the acceleration down here at the bottom. And it's because that velocity goes to 0. And rho would just be the radius of the string. And so that's the idea that we're looking at there. Now, this is coming to play in a whole host of applications. And so one of my favorite is the Texas Motor Speedway. Okay, the Texas Motor Speedway is a NASCAR race, and the cars are intended to. NASCAR goes at a little over 200 miles an hour at the top. And Texas Motor Speedway was built with some very large banking curves so that those NASCAR's cars could stay at close to their maximum speed through the turn. Well, they tried to do a kart race, an Indy 500 style race with these open-wheeled racers. Well, these open-wheel racers have a lot more downforce and they can go a lot faster. And what was happening is they were going through those curves, they were experiencing excessive normal force. Their velocity had gone up by a lot to over 250 miles an hour. That was 250 miles per hour is pretty close to their average speed for the lap. And so they might have been around that, certainly faster than that in the straighter ways. But they were experiencing about 5 Gs. So they were getting a little lightheaded as they were going through the curve. Basically, they were turning too fast. And we've experienced this in our car, right? If you're driving along and you turn sharp, you like slam your passengers up against the window, right? And if you take a nice gentle turn, there's no problem there. And so what I want you to think about is if you were in charge of this race, they ended up having to cancel it but I can think of at least 3 ways that we could decrease the normal acceleration so that they could have a better race. And so I want you to think of those ways, post them in the discussion on our Canvas, Citadel Online, and then we'll talk about it in class, as well as work a problem from our Judge Roy screen. So I look forward to seeing you in class. Thanks.